All right, in this video, I'm going to talk to you about quantum theory and the Bohr model. So, here is the model of the atom, where we left off in our last couple videos with the history of the atom. We had Rutherford and his experiments with the gold foil. This is the model, right? We have electrons and they're orbiting around this dense mass called a nucleus. This model was challenged almost immediately because there's an issue with charged particles. When they accelerate or when they go around in a curved path, they emit light and lose energy. That's the idea behind TVs, and we even talked about the cathode ray. This was a serious issue because then electrons would almost immediately lose all their energy. Okay, so this one's going to make your mind hurt a little bit, and I'm going to do my best over the next few videos to help you understand quantum theory and the quantum mechanical model of the atom. Get ready. Electrons are not orbiting perfectly around the nucleus. This represents what electrons are really doing. And to understand this, you need to understand a little bit about quantum theory. So, Max Planck was a German physicist who began to come up with these ideas of wave-particle duality. And basically, energy had long been considered a wave phenomena. Max Planck showed how particles can actually act like waves using these very precise but discrete and exact units of energy, packets, known as quanta. So, let's go talk about Niels Bohr. Somebody I've mentioned before. Even at the beginning of this course, I've talked about Niels Bohr. All right. He was doing some work with emission spectrum or atomic spectrum. All right. What this is it's a very unique pattern of light, almost like a barcode, that's obtained when an element is subjected to like energy like heat or electricity. Okay, look at what he observed. This is what he's very famous for, his work with hydrogen. And where he went with this is spectacular. This is the atomic emission spectrum for hydrogen. Now, you would think when you look at it, you would see like a rainbow of colors. But using a spectroscope, Niels Bohr observed discrete. You see where I'm analogous to a barcode. You see the 4 lines on this spectrum. And this is what hydrogen looked like always when it was subjected to energy, like heat and electricity. This spectrum would appear. And if we look at other elements, like helium, it has its own unique atomic spectrum with its own unique barcode. So something's going on here, and that's where Niels Bohr began to really question some things. And he looked specifically at hydrogen, and he proposed that electrons are not orbiting due to the flaws back then in that logic and the loss of energy for an accelerating charged particle like an electron. He said that these electrons are actually in clouds around the atom, and I'll expound here in a minute. Bear with me over the next few videos that these electrons were located in clouds, okay? That they would occupy a definite orbital and require electrons a specific amount of energy. So they do have these circular orbitals, but they have specific quantized energy. That's what Niels Bohr was proposing. Okay, so when electrons, and this is a critical piece for you to pick up on, when electrons absorb energy, okay, and remember that's what Niels Bohr was looking at through the spectroscope, was looking at hydrogen when it was hit with either heat or electricity. All right, so when electrons absorb energy, they will jump to a higher energy level. They will jump to a high energy state. And this is known as the excited state. It's a high energy, unstable state. It results from an input of energy, heat, electricity, light. Now, subsequently, those electrons will fall back to ground state, which is a lower energy state, a lower energy level. When electrons become excited and fall back to ground state, they release the energy they absorbed in a packet of light called a photon. Okay? So when you look at this schematic, try to make some sense out of it here. We have an electron orbiting around the nucleus. Then we see an input of energy, causing that nucleus to then jump to an outer energy level. And then, as it falls back down, you see it emits energy, and that energy is light, and that light is in a packet called a photon. It was later called a photon. Niels Bohr didn't call it a photon, but that's what we call it now. Okay? So, here's another breakdown of how this works. Electrons can only move between specific energy levels. Discrete, see these words keep coming up, energy levels. Okay? This means they can only gain or lose these discrete, exact, precise amounts of energy. This form of energy is known as quantized energy. Now you see back going to Max Planck, he called those packets quanta, okay? Now quantized energy levels are very exact. If you look at this diagram, what can this one electron do? It can only move this far. It can jump that far, and it can fall back that far. There's no intermediate, and that's where I mean discrete, okay? So these quanta, these quantized energy levels are called n equals 1, n equals 2, n equals 3, and so on. This schematic here goes out to the third energy level. So we see here that this electron can jump out to here, but when it falls, and that's what the green light line is showing, it emits something called a photon, light, a very specific light. So think about the atomic spectrum, the barcode. Think about the pattern there. That's all Niels Bohr saw when he looked at the hydrogen. Those 4 spectral lines, that was it. Okay? Now in this case here, this can jump 2 energy levels out. It can fall 1 energy level or 2 energy level, but nothing in between. So it can absorb that much energy, or it can release that much energy. All right. So these quantized packets or photons emit specific wavelengths. Now here, I'm putting them both together. You've seen the atomic spectrum. You've seen the model of the electron orbiting in a circular cloud. And you've seen how those electrons are essentially jumping or moving up and falling down. Moving up, falling down. In this case here, moving up, 1, 2, 3, 4, 5 quanta, okay, all the way out, falling 1, maybe falling 2, maybe falling 3. All right, so if you look at this schematic and look at these lines, you can see how the lines correspond to different energies. Now remember, the shorter the wavelength, the greater the energy. All right, so we have a 656 nanometer and a 410. That 410 has a tremendous amount of energy, relatively speaking. Okay, and look how far it is falling when it falls to ground state and emits that quantized packet of energy, that photon. Okay, so Niels Bohr's work, it helped to explain the atomic spectrum, which again didn't make sense because you'd think you'd see a rainbow. And it explained why they have unique patterns. You guys, scientists today study stars by using spectroscopes and studying the atomic spectra emitted from planetary objects. And from that information, they're able to determine the elements that are on planets in outer space. So this was an attempt to give you a good idea and lay a foundation for the quantum mechanical model of the atom. I'll see you guys in class.